Hi everyone, today we're going to go through functions and the very basics of object-oriented programming and how to essentially define objects in Python, how to use them and why they are useful. We will also start with going through the basic data types, how to manipulate lists and strings. Enjoy! Okay, let's get started. The first thing we're going to do is we're going to set up a new virtual environment in our new project folder, Python 3-m for module, venv is the module name, and then the second venv is the folder name where we're going to put the virtual environment. Then we're going to start it by using source venv bin activate. And then we're going to install Jupyter. pip3 install Jupyter. Let's go, I just did it, that's why it's super fast here. And then we're going to start Jupyter. This time we're not going to use Jupyter Notebook, but this time we're going to use Jupyter Lab. Which essentially is the same thing. With the exception that you have a nice navigation bar on the left. And it's a bit easier to handle multiple notebooks. That's why I actually prefer Jupyter Lab. Okay, Control M, like Mickey Mouse, and then the B key adds new cells. And then we're going to change the first cell to Markdown, and then we are going to use the Markdown language, so essentially using hashtags to give the whole thing heading. We can put a heading here, let's say Introduction to Object-Oriented Programming. And then with Shift-Enter, you execute a cell. And then if you want the next cell to be code, you just select code again. Okay, so we start with going through the very basic data types. So you can have booleans. For example, A is equal to false. And B is true. These are the very basic booleans, and you just declare them with the equal sign. You don't need anything preceding A. Usually, like if you were programming C++, you would have to do something like this. In Python, you just do it like this. This also means that A is a dynamic object, so you can actually say A is false here and A is 1 here. So you can cast an integer to the same variable. Okay, speaking of integers, integers, as the name says, are integer numbers. In Python, what you can do to make things more readable is you can throw in some underscores here. This does the exact same thing as doing it without underscores, just the next programmer who will read your code will have a much easier time understanding what's going on here. Good. Then next up we have floating points. For example, everything that has a dot something is a floating point. The point of floating point is to be able to express numbers between the integer numbers, but you have to be very aware of that they have limited precision. So the problem is, if you want to express numbers in powers of 2, as computers do, there's only so many numbers that you can squeeze into a memory block that is picked for floating point numbers. So that means that if you go to very, very small numbers, so something like something like this, and you add 2 of them together, you might not get exact results. But that is actually never really a problem, because you can always rescale the thing you're predicting. Say you're predicting the distance, or you're doing calculations on the distance from here to your next shopping mall. if you calculated the distance in light years, that would be 0.00000 something light years. But if you did your calculations in, say, meters or kilometers, then you wouldn't get into this type of trouble anymore. So be aware that the precision of this is roughly 10 to the minus 8, depending on how big the floating point numbers are that you use. So 32-bit is the standard that is used in Python, but for most of the things you can actually cast it down when you use special numeric libraries to 16-bit. So to numbers that actually use half as much memory, but also only give you, I think it's a factor 4 of precision. Okay, let's get back to floating point numbers. So what you can do, instead of writing them out like this, you can also write, let's say 12 minus 8. So e gives you an exponent, so you can do something like this. So you see this is 1.2 e to the minus 7. If we did 3, you would get this. So those are the very basic data types. Next we have strings. Strings are essentially strings of characters, even though a single character already is a string in Python. Let's say A is A, and B is B. Then they offer very basic operators, say S is equal to A plus B, and you see the result is just A plus B, so merge the strings together. These are normal strings. You can also make, longer strings, obviously. Then you can use format strings. So let's say formatted string is equal to something. You specify that it's a formatted string, formatted string with this f here. And what you can do with formatted strings is you can put variables in. So you could say something like value of a is, and then these brackets here specify that you are putting a variable. So we could put a here, and then we just say a is 1.234. And if we print this, we get 1, 2, 3, 4. The next step would be to format this even further. So what you can do is you can do something like this. 0.2f takes nothing in front and the last 2 digits after the point, and then assumes it's floating point. And what this does precisely is it cuts away everything behind the last 2 points, for example. This is very neat if you want to format them for nice printouts or something like that. What you can also do, what you see, the 4 was rounded down. If we go to 5 and do this again, now it's rounded up. So from 5 onwards, it rounds your floating points upwards. Then what you can do is you can access these strings with a simple list access. We will have a look at lists in a moment. But essentially, this is a list of characters. And now you see the 6th character is A. So 1, 2, 3, 4, 5, 6 is A. Another thing you can do with strings is you can split them. So we can split the string, dot split at another substring. So say we split this at off. And then what you get is a list of strings. And the first parameter is everything up to here. And the second one is everything up to here. So string operations are very, very easy in Python, whereas you would have to write a lot of code in C++ to do something like this. Okay, we already mentioned lists before. A list you specify like this with sharp brackets, and then you can put in whatever you want. So this is an empty list. And then you can put in an integer, a floating point, a string, a bool, and maybe another list where we put 2, 3, and the word 4. You index a list simply using index brackets like this, and then you can say 0 for the first element, -1 for the last element. You can also do -2, which is the second to last element. And you can say all elements, or you can say everything from second index onwards, so from this onwards, or everything up to the second, everything from the first to the second, so 0 would be the first if you wanted the first. So yeah, this is how you can slice lists. This is very nice, in my opinion. And then you can do stuff like, say, we want this list here. This is 1, 2, 3, 4, 5. So list index is out of range. Oh, I'm done. 1, 0, 1, 2, 3, 4. And if you want something out of this list, you just index it again. So you do 1 for the second element, and you get this 3 here. Then you can append to lists. Append this does it in place, so you don't have to say L is equal to. So you don't do L is equal to this, but you do this in place. So now I added another thingy here. If you have a second list, let's call this L2 is equal to 1, 2, 3. And then you can do L.extend L2. So this will not put 1, 2, 3 as one element to the list, but it will go through all of the elements of your second list and will append them. So this is very useful to know. And then there is a function called len that gives you the length of lists. And just one more thing, if you have a list that is empty, has a length of 0, and if you have a list of 1, has a length of 1. And then the last thing we have to speak about are dictionaries. And dictionaries are mappings. Essentially, mappings are mappings of key and value pairs. So you can say Joe, that's my name, maps to 1. And if you print this, you get the whole thing. Let's say Tash maps to 2. So if you now access this, you access it the same way you would access a list, but with the key. So let's put Joe here, and then you get a 1. And if you put Tash here, you get a 2. You can also do whatever you want. Actually, I've never tried bool. So let's see what this does. Ah, this also works. So you can map whatever value you want here to here. One thing you have to have in mind is that the key must be unique. So if you say D of false is 5, now you print D again, you see it updated the value here. And this is where actually this becomes very useful. However, it's very confusing if you mix the data type of your key. That's why you should always have the same key data type. So strings mapping to something. What you map to doesn't matter so much, but the key should be at least the same data type, even though Python doesn't enforce it. But if someone else reads your code, this would be hellishly confusing if if you had different data types mapping to other things, unless that's specifically what you use this mapping for. If you want to access keys and values, they have functions that provide these. So the keys gives you all the keys. The values gives you all the values. 1 empty and 5. Now it makes sense. So 1 and empty. And then you have items that gives you tuples. So key and value pairs. So these are essentially lists with a fixed length. So if you specify a list like this, now you can't append. Because tuples don't allow to make them longer. That's why you get this as a list of tuples returned here. Okay, let's have a look at if and for statements. These are very basic conditional statements. Let's say A is true. And then you can do stuff like if A is true, print A is A. And then you can have else statements. Else, these are not mandatory, as you just saw. Now A is false. You can abbreviate this a bit. And let's say A is a list. 1, 2, 3, 4. 1, 2, 3, and then you can say if len A larger 2. Print A essentially. So here you see this is what this is actually used for. And you can also say elif exactly 3. Nah, my fingers don't want as I do today. And it must be like this. Print. Hooray! So now you have 3 conditions there. But what you see now is the first condition that applies is a hit. So if this hits, then this is not going to be checked. So what you have to do is something like this. So now you see, okay, it's exactly 3. It's larger than 3, so this doesn't hit. And now this is executed. Yeah, this is how you use if statements. Now we're going to have a look at for loops. Let's say we have a list of names. Peter, Parker, Spider-Man, and Aquaman, whatever. For, what you can do now is loop over this list. So with a for loop, you can do for name and names, print name, so that you can do something with the object that is in there. See, and now it goes through all of these, maps it to name, and in every single iteration, so in every step of this for loop, name is equal to this object in here. So what you could also do, if len name larger, let's say 6, print hooray. Actually, let's just print the name. Something I haven't shown you so far is you can also do comma separated. Name again. This is a bit uglier actually. So you see, name again. Spider-Man is larger than 6, simply because it has more than 6 characters. This is how you use for loops for existing list. What you can also do is you can use for loops in a more numerical way. So what you could say is n is 10, and then you can do for I in range n, print I. So I will be turned into an integer while we walk through the range. So what this is doing is it starts at 0. It says I is 0, I is 1, I is 2, etc. Yeah, this is very useful if you want to do whatever with an increasing I, for example. What you could do now as well, you could do i's. Is an operator, that's why we put an underscore here, just to make it more pretty. So we now defined an empty list, and then we say i's dot append I. And now we have a look at what this is. And you get a list with all the values of I. However, you will most likely never see something like this, because in Python there's something called a list comprehension that gives you the ability to squeeze stuff like this into one line. So what you can do is you can do every element of this list, so every I is just going to be the I itself. So I for I in range n. So what this does, it puts every I in this list for I in range 10. 100. Let's say 10. Actually, let's copy this over. And now let's have a look. And yeah, this is a much more condensed way than doing it like this, because here you need 3 lines and this you can do in 1 line. That's why you will most likely always see this and almost never something like this. Next thing you can do is you can put if statements in here as well. So you can say if I is less than 5. You see, now it only put I in the list if I was less than 5. So no matter what we put here, it will always be this list here. You can now do the same thing with dictionaries. So now we're going to define a dictionary. We do it the same way, just with curly brackets. And then we have to map these values to something. So let's say 1, Parker is 2, Spider-Man is 3, and Aquaman is 4. And now there's multiple ways of looping over this. So what you can do is for key and value, so let's actually be explicit, key value in names.items. So here you see where these functions that I showed you earlier come in handy. Print key is key and value is value. And you see now it prints out all these pairs. You could also just be very simple and do something like keys. And then you throw away the second one here. You just do it like this. And yeah, so you could, for example, do something like this. Let's say we want all of these ones to be lower letters. So let's say we put a capital K in here for whatever reason. Then we say keys is equal to, this is going to be a list, key dot lower for key in, what's the thing called, names dot keys. And now you see something funny, because the last value for key in this loop was Aquaman. That's why still Aquaman was written in key. And here I only put key, but here I call it K. So it wasn't really written. So what I have to do is I have to name it key here. And then you get all the names that were in here with the function lower called on them. So if you do something like a function like this on the string, it does this. There's also a upper, by the way. Now that we have the very basic types covered, we will have a look at writing our first functions. So in order to write a function, you have to define it. You just write def, and then you give it a name, my function. And then in these brackets, you put the arguments of the function. So let's say x and y. And then you have to put the code in your function with a tab. So everything that will be within the namespace of the function, so to speak, will be here. So let's say x squared is equal to x times x, and y squared is going to be y squared. So this does exactly the same. This double star operator, like in Fortran, is a to the power of operator. However, it's actually much faster to call x times x than calling to the power of, because it has to look up this power of operator twice, while this operator just looks up once and then looks up the value already. So if you want to write something like this, just stick to writing y times y. Oops. And then you can do return x squared plus y squared. So this now just defines the function. If you want to call the function, you take the function, and now there's two ways of doing this. The lazy way is to just put in 1 and 2, and then the function will figure out that the first argument is going to be x, and the second is going to be y. And then it will return something. So here it's being directly thrown onto the console because it's not written to a variable. If you want to write it to a variable, you do that like that. And then you could do result. A cleaner way would be to do something like this. That's the exact same thing. It's just more readable because now you understand what 1 and 2 is going to be put in. If you have more complex functions, that's sometimes easier to understand. However, the downside is you can imagine if these x and y become very long names and you have like 10 arguments to a function, this becomes a very long line. So you need something that breaks this into multiple lines. Okay, and in modern Python, people usually also do type hints. So you can do int and int here. And that would tell only other programmers, okay, what x and y are going to be is integers. This is not being enforced. So if you put in a float, Python also accepts this without complaining. So these type hints are really just hints for other programmers. And if your function does not return anything, so if we comment this out, it seems to have something returned, and that is none. So a function always returns, even if you don't return. What this does implicitly is it does something like this. Return none. Oops, not 9, none. And by the way, this is how you check for equality. You can also do... Okay, so this is a function. One more important thing. Y squared is not known outside of the function. So this variable that we specified here is only known inside the function. So that's why we need these arguments actually, because we put them into the function so that the function knows what x is and also knows what y is. And outside of the function, we do not know what x and y is. That's absolutely necessary because otherwise you would run into a hell of having the same names for everything. Imagine you work with 10 programs on a project and everyone calls their variables x. Yeah. However, what you can do You should not do this, but you can. That's just why I'm showing it. You can put stuff outside. Let's say x squared is equal to 5. And we chuck this away. Result. So the function knows about this global variable because now x squared is known on this namespace, so the namespace in which also the function is written. However, you should never ever do something like this because this is going to be very confusing, because if you now copy this away, now this doesn't work anymore. Actually, within Jupyter this works, but if you did this in a Python script, this wouldn't work. In Jupyter this works because x squared is known in all of the cells. However, if you did that in different Python files, they would not know. And it would also be very hard for another programmer who reads your code to understand where x squared is coming from, because it's not nowhere in this function here. So you should always, always, always put all the stuff that you use in this function. Yeah, in JavaScript you might see this sometimes, that they use stuff from outside of the function, and it's very, very confusing, and in my opinion it just shouldn't work. But yeah, in Python it works, so that's why I tell you. One more thing I want to add about functions is you can put in the values of a function as a dictionary. So what you could do is you could do values is equal to a dictionary, where you say x, this must be a string, 1.7, and let's say y is equal to, oops, 2.5, and this must be a string. And then you can take the values dictionary. Let's put this in a different cell. And dereference the values. Oh, and this must be a, whoops, lots of mistakes here. Oh, interesting. This doesn't work. But what you can do here, this works. So what this does, it unpacks packs your dictionary. So it takes this dictionary here and then figures out, oh, x is mapped to 1.7. So what he meant is x is going to be this value and y is going to be the other value. So sometimes you might see this in a kind of writing like this, quarks, for keyword args, and then they just do stuff like this. However, this is fairly advanced, and whoops. As a beginner, you shouldn't do stuff like this. It's just that you are aware that this double star notation means unpack this dictionary and stuff it in here. We will now speak about objects. Object-oriented programming is sort of the holy grail of programming. It's still the most commonly accepted way of abstracting code. The problem is, if you write abstract code, it must be written in a way that others are still able to comprehend it. And not only to comprehend it, but also to comprehend it in a kind of timely way. So, I mean, you can understand assembler if you read it, but it's going to take you ages to actually figure out what's going to happen. Objects give you a way of abstracting things in a way that kind of tell a story and kind of tell the programmer what the hell is actually going on. So objects are extremely important. The first concept that you need to understand is the difference between a class and an object. So class is a blueprint, class in terms of mathematical category theory, actually. So a class is a classification, so it's defining a type. Whereas an object is an instance of a type. So an object is like a house, whereas a class is the blueprint of a house. Let's make this a bit more clear by writing some code. So in Python, you define a class by just writing class, and then you can type a name, say mammal. And then we define an init function. In other languages, this is called constructor, that constructs the actual object if you build it. So what we can put in here is unique values for this thing, whatever this thing is. In this case, it's a mammal. So what we can do here is we can put in self.number of legs. This defines an attribute of this class. Let's say 4. Most mammals have 4 legs. And now we can access this by just calling it via the dot notation. So first we create an object. So this is a class, while an object would be, say, mammal is equal to mammal. So classes always start with a capital M in Python, just so that you have a very easy time distinguishing them from functions, because functions never start with a capital letter. And then these 2 brackets here call this init function. So if we do this, this code here is going to be executed, and it's going to set this value. This self here means that this is referring to the class. So if you put a function in here, you always have to give this self value in order to put stuff in these fields. Where this is becoming handy, I'm going to show this in a moment. But this is how you build an object. So this is an object, while this here is a class. And this here is a type. I hope that is clear enough. So let's have a look at the properties of this. So let's say we have a look at number of legs. You see, you can just access this with the dot notation, and now this self here is referring to this instance of this object. What we could do is we could put a parameter here, let's say n legs, and put it here, just for the sake of demonstration. If we now build this object, it complains because we didn't give it the parameter n legs. So what we can do is we can say n legs is equal to 4. And now we get the same result. What we can now do is we can still have... let's first show you how to do this with the default parameter. So you can put a default parameter in here, get the same, and now we can leave this out just for the sake of demonstration. Zack, still get the same. Now we have a, let's call this normal mammal. Now we could say injured mammal, and for some reason this guy only has 3 legs. And now you see, because we accessed the normal mammal. So you see, these are 2 different instances, normal and injured. Injured mammal. Injured mammal is not defined. Oh yeah, because I have to execute this line first. So you see, they both have the same type, that is mammal, but they are different instances, because this one here has this field set to the value 4, while this one has it set to the value 3. So this is how you can use different fields. Next thing is, we can define functions for these mammals. Let's say get nlex. If you define functions for classes, you also have to pass the self parameter, because what you can do now is nlex is equal to self.nlex, and then return nlex. So you see, this self here helps you to reference fields that were built at construction time of this object. You can also reset them, so you can, I don't know, do something like this. Heal, whatever heal means. And then you can set this to 4. So if we want to call this function get nlex, we can do the same thing here. We do injured mammal dot get nlex. So in other languages, you cannot directly access these fields. That's, for example, in Java, you would always have a getter function for this. In Python, you can. However, this is just to demonstrate to you what this self thing does. So, yeah. So you see, this is how you define functions on objects, or in classes on their objects. And now what we could do is dot here. And now it has 4 legs again, because this heal function sets the value of this field to 4. The last thing we're going to have a look at is inheritance. Inheritance is a way to inherit properties of one class to other classes. This gives you the ability to abstract away certain functionality, and also to organize your code in a very easy to understand way. So say you have, for example, something that's accessing a database, and you're going to reuse that object everywhere in your code. So what you could do is you could abstract away the part that is always reused, and then inherit forth the stuff that you need to change or make specific for specific use cases. And we're going to do an example on that, and then you see why this is very powerful. So we're going to start with an object called mammal again. This thing has a constructor, self, and we're just going to care for one parameter here, that is the name. Name is equal to name. And before we continue, we'll have a little detour. There's an inbuilt function called string. This is a Python built-in function, and that you don't have to import or anything, you can always use it. And it's used to turn stuff into strings. For example, if you don't put anything in it, it gives you an empty string. If you put in an integer, it gives you the integer as a string, and if you put in a float, same thing for a float. You could also put in, any primitive type essentially. But what if you want to turn our mammal into a string? So let's say mammal. Let's create an instance of this class, mammal. This guy is called Peter. Let's see what the string of mammal is. So what this gives you is, because it doesn't really have any information available, you just can tell, okay, it's a file called main, that's a Jupyter thing. It's an object called mammal, and it has a memory address of so-and-so. Yeah, but is this really the string of a mammal? I don't know. So if I wanted to implement my own string method, I would do it like this. Self. And then we can put something more appropriate. So for example, this mammal's name is self.name. And here you see where this self thing becomes in very handy. So you need this self here in order to refer to something that is not defined within the function. Because it's defined here, we access it through the self field. So this is how it works. And this is a format string with the f, so that we can put this value in here. I mean, you can put whatever here. I just want to demonstrate that there's certain special functions, for example, for the string method, that you can implement yourself if you want to. So this now prints this string that we just defined. So back to inheritance. So say we have a class dog that inherits from mammal. So here you put in the class that you want to inherit from, for example, this mammal here. Then you have to define a constructor again. Constructor tells Python how to build this object. In this case, let's put in a name again. And then we have to call the constructor of mammal, because how else would we define name for this name here to work? So you call super. Super calls this thing here. And then we call on super, we call the init function. And then we pass the name in again. So this way, if we create a dog, we have to pass a name, obviously. Let's call this dog Rex, because all dogs are called Rex. Dog dot, actually we want to call string on this dog. And you see this string method now was inherited through to dog. So if we wanted to have another class, say a cat, can have now all sorts of things inheriting from mammal. For example, cat. We can now do the same thing. Let's say cat's name is Björn. That's the neighbor's cat name. Won't give you mine, because then you could do social engineering and steal my passwords. You see, this way you can get properties through to other classes, and this makes it very easy to abstract away stuff that you would otherwise have to implement for dog and for cat. So this way you get this function here in dog and in cat. So now we can go ahead and implement our dogs and cats. I say the dog is a bark function, obviously. That does nothing else than print bark. And in the same way, the cat has a function called meow. And now we could call, first we have to redefine the objects so that they are updated with what we just did. Let's say cat.meow. Meow. and dog.bark. So cat and dog are now completely independent objects, but kind of inherit the functionality of mammal. And this allows you to build very complicated cathedral-like structures. You see, if we wanted to extend this now, we could give this mammal another function. For example, as we did earlier with something like get number of legs. So now we have a very easy way of extending these two classes without actually touching them. So we can now do inherit again, execute all of this stuff, and do dog.get number of legs, and we get the 4 that we returned here. You see, this is how this can be really, really powerful. However, usually all of the stuff that I showed you today is usually spread out over at least half a year's worth course material of university. Yeah, that's it for today. I hope you enjoyed what we did. We went through a lot of stuff. Just one final remark on how to kind of get this into a proper workflow. So as you see, we prototyped everything in Jupyter and always had a look what we get when we execute those functions. And this is how I usually work. So I prototype my stuff in Jupyter, and once I'm sure the classes and objects do exactly what I think they do, then I just copy this stuff into Python files and kind of build my folder and a Python file structure from there. Yeah, thank you very much for listening. Have a good one.